Tonight, we are going to try something impossible. We are going to try to understand the size of the universe, not just hear about it, not just nod and say, yes, it's very big. I've heard that before. We are going to feel it, and we want to warn you right now. It is going to break something inside you, something small, something comfortable. The little voice in the back of your mind that says, I understand the world I live in. That voice is going to go very quiet tonight. There is a number that scientists use when they talk about the observable universe, the part of space we can actually see, the part bound by the speed of light, the age of time, the laws of physics as we know them. That number is this: 93 billion light years across. Now we're going to say that again, and we want you to breathe for a moment before we do. 93 billion light years. A light year is not a measurement of time. It is a measurement of distance. It is how far light travels in a single year. And light is the fastest thing in the known universe. Light travels at 186,000 miles per second. Per second. In 1 second, a beam of light could travel from here to the moon and back again, more than 7 times. In 8 minutes, that same beam reaches the sun, 93 million miles away. In 4 years, it would reach the next nearest star. And the observable universe, the universe we can see, is 93 billion light years across. Let that settle. Let it sit in your chest like a stone. Because here is the truth that we are going to spend tonight uncovering together. That number, 93 billion light years, is not the whole universe. It is not even close. We don't know how big the real universe is. We don't know if it has an edge. We don't know if it goes on forever. And we may never know, because the universe itself is expanding faster than light can cross it. There are regions of space that are racing away from us so fast, so relentlessly, that no signal, no message, no photon of light will ever reach us from there. They are gone, not destroyed, just unreachable, forever. That is where we are tonight, sitting on a pale blue dot, wrapped in 4 billion years of evolution and memory and hope, looking out at a darkness so vast that our minds were simply never built to hold it. But we're going to try. We're going to go out there together, in the dark, in the quiet of tonight, and we are going to look. Before we go, if this is the kind of journey you want to take again, if you want more nights like this, more of the cosmos and its impossible truths, subscribe to this channel. Hit the notification bell, because we do this regularly. We come here, into the dark, into the mystery, and we think you belong here with us. Now, let's begin. Let's start small. Let's start with something we know. Let's start with home. You're here, somewhere on the surface of a rocky planet, third from a medium-sized yellow star, in the outer arm of a barred spiral galaxy called the Milky Way. Right now, as you listen to this, you are moving, even if you feel perfectly still. The Earth is spinning at roughly 1,000 miles per hour at the equator. It is orbiting the Sun at 67,000 miles per hour. The Sun, pulling us with it, is orbiting the center of the Milky Way at 514,000 miles per hour. And the Milky Way itself is hurtling through space toward a region called the Great Attractor at over 1,000,000 miles per hour. You're never still. You have never been still. Not once in your entire life. Now, the Earth. our home, 12,000 kilometers in diameter. If you could drive a car at highway speed around the equator without stopping, it would take you about 2.5 weeks. That feels big. That feels enormous. Now look at the sun. The sun is so large that 1.3 million Earths could fit inside it. Not around it, inside it. If the Earth were the size of a marble, the sun would be a beach ball about 6 feet away from it. And the sun is not a particularly impressive star. In the catalog of stars, the sun is average, medium, ordinary. There are stars in our galaxy called hypergiants, so enormous that if you placed one where our sun sits, its surface would extend past the orbit of Jupiter. The star Scuti, one of the largest known, has a radius nearly 1,700 times that of our sun. If Scuti were our sun, we would be inside it, deep inside it, buried in stellar plasma, incinerated, erased. But even Scuti, monstrous and almost incomprehensible, is just one star. One. Out of how many? In our galaxy alone, the Milky Way, our home spiral, there are estimated to be between 200 and 400 billion stars. 200 billion. Let's try to feel that number. If you counted one star per second, without stopping, without sleeping, without eating, without pause, it would take you over 6,000 years to count to 200 billion. You would have started counting before the first pharaoh sat on the throne of Egypt, and you still wouldn't be done. That's just our galaxy. The observable universe, that sphere of 93 billion light-years we talked about, contains an estimated 2 trillion galaxies. 2 trillion, not billion, trillion, with a T, 2 trillion. Each of those galaxies contains, on average, hundreds of billions of stars. So when we try to count the total number of stars in the observable universe alone, astronomers estimate it as something like 200 billion trillion. 200 billion trillion. Written out, that number looks like this: 200 quintillion. There are more stars in the observable universe than there are grains of sand on every beach and every desert on Earth. More stars than grains of sand. More stars than every breath ever taken by every living creature since life began on this planet. And around many of those stars? Planets. We know now, thanks to missions like NASA's Kepler Space Telescope and TESS, that planets are not rare. Planets are common. In our galaxy alone, there may be more planets than there are stars. Some estimates suggest there are 100 billion planets in the Milky Way. Others go higher, much higher. Some of them are in what we call the habitable zone. Not too hot, not too cold, possibly with liquid water, possibly with conditions that life, as we understand it, might find comfortable. Billions of planets in our galaxy alone, and there are 2 trillion galaxies. We want you to sit with that. We want you to really, truly sit with that. Because what it means is this: the universe is an almost unimaginable ocean of matter and energy and time. And we are on one small planet, orbiting one ordinary star, in one average galaxy, in one corner of one observable slice of something that may go on without limit in every direction whenever. Now, here is where the scale stops being merely impressive and starts being unsettling. The universe is not just big in space, it is big in time. The Big Bang, the birth of everything we know, the moment space itself began to expand, time itself began to tick, energy itself began to flow, happened approximately 13.8 billion years ago. 13.8 billion years. Our Sun formed about 4.6 billion years ago. Earth formed shortly after, about 4.5 billion years. Life on Earth began roughly 3.8 billion years ago. Complex life, creatures with more than one cell, only appeared about 600 million years ago. Dinosaurs walked the Earth 230 million years ago. They were wiped out 66 million years ago. And us? Modern humans, Homo sapiens, with our language and our fire and our art and our longing to understand the cosmos, we appeared somewhere around 300,000 years ago. If the history of the universe were compressed into a single calendar year, if the Big Bang happened on January 1st at midnight, then our Sun wouldn't form until early September. Earth would appear in September as well. The first life on Earth? Late September. The dinosaurs? December 25th, Christmas Day. Their extinction? December 30th. And all of recorded human history. Everything from ancient Mesopotamia to the moon landing to tonight, right now, you listening to this, fits inside the last 14 seconds of December 31st. 14 seconds. That is our entire story in the context of cosmic time. We are new here. We are astonishingly, almost embarrassingly new. We arrived at the party of the universe 13.8 billion years after it started. And the party, by all estimates, is far from over. The universe will continue to exist, in some form, for perhaps another 100 trillion years. Maybe longer, maybe in a sense that stretches the word beyond recognition, forever. Which means that in the entire story of the cosmos, we are not even in the opening credits. So we know the stage. We know how vast it is. We know how old it is. We know how many stars and planets and possibilities exist within even the small slice we can observe. Now let's talk about what we've found and what we haven't, because this is where the mystery begins to deepen. This is where the size of the universe stops being just a number and starts being a question. In 1977, a radio astronomer named Jerry Eman was working at the Big Ear Radio Telescope at Ohio State University. He was part of a SETI project, the search for extraterrestrial intelligence. His job was to scan the sky for unusual radio signals. Signals that might not have a natural explanation. Signals that might come from somewhere or someone deliberate. On August 15th, 1977, the telescope picked up something remarkable. A signal so strong, so structured, so unexpectedly precise, that Eman circled it on the printout in red ink. Next to it, he wrote one word: wow. The wow signal, as it came to be known, lasted 72 seconds. It came from the direction of the constellation Sagittarius. It matched almost perfectly the expected profile of an interstellar transmission. It was never detected again, despite decades of listening, despite thousands of hours pointed at that exact region of sky, despite the most sensitive instruments ever built. It was there for 72 seconds, and then it was gone. And we have been listening ever since, in silence. That is the wow signal. One data point in nearly 70 years of searching. One 72-second burst of something that we cannot explain and cannot replicate. And then nothing. But the wow signal is just one anomaly. There are others. There are many others. Let's talk about Tabby's star, or as it's formally known, KIC 846282. a star in the constellation Cygnus, about 1,500 light-years from Earth. In 2015, astronomer Tabitha Boyajian published a paper about this star that made the scientific world pause and lean forward. The Kepler Space Telescope had been monitoring KIC 8462852 for years. Kepler's job was to watch for tiny dips in a star's brightness, caused by planets passing in front of it. Most stellar dips are small, predictable, regular. A planet-sized object might block about 1% of a star's light. KIC 8462852 was doing something else entirely. It was dimming, by up to 22%, in irregular, asymmetric bursts. Patterns that no planet could create. Patterns that no natural, known stellar phenomenon could easily explain. Astronomers scrambled for answers. Comets? Possible, but unlikely to produce such massive, irregular dimming patterns. Interstellar dust? Maybe, partially. But one hypothesis, the one that made headlines, the one that made people look up at Cygnus and wonder, was something called a Dyson sphere. A Dyson sphere is a concept first proposed by physicist Freeman Dyson in 1960. The idea is this: a sufficiently advanced civilization, needing vast amounts of energy, might build a massive structure, or a swarm of structures, around their star, to capture as much of its energy as possible. A stellar megastructure, built by minds we cannot yet imagine, with technology we cannot yet conceive, at a scale that dwarfs anything in human experience. If such a structure were partially complete, being built piece by piece over centuries, it might cause irregular, dramatic dips in starlight, exactly like what we observed at KIC 8462852. Now, scientists are careful. Scientists are cautious. The current best explanation for Tabby's star involves interstellar dust and unusual stellar behavior, not aliens. But the possibility was real enough to be considered. The data was strange enough to ask the question. And that question, once asked, does not go away. Let's talk about the Great Void. The Bode's Void. Imagine the universe as a vast cosmic web. Galaxies clustered along filaments of dark matter, like dewdrops on an enormous spider's web. Between those filaments, vast, mostly empty regions called voids. The Bode's Void is one such region, found in the constellation Bode's. It is approximately 330 million light-years across, and it contains, compared to the surrounding cosmic web, almost nothing. A handful of galaxies where there should be thousands. Astronomers sometimes call it the supervoid. It is so empty, so anomalously large, that when it was first discovered in 1981, some researchers struggled to explain it within standard cosmological models. One astronomer, Robert Kirshner, described the feeling of finding it. If the Bode's Void is someday found to be the work of a technologically advanced civilization, we wouldn't be too surprised. He was probably joking, but the void is real, the emptiness is real, and the models that predict how matter should clump and cluster in the universe have to work very hard to explain how such a vast, clean emptiness came to exist. Then there are fast radio bursts, FRBs. Fast radio bursts are some of the most energetic and mysterious events ever detected. They are extremely brief, lasting just milliseconds. A millisecond is 1,000th of a second. But in that fraction of time, they release more energy than our sun emits in 3 days, sometimes more. Most FRBs have been detected just once, from a specific location, and never repeated. But some, called repeating FRBs, have fired multiple times from the same source. Some of those repeating bursts show patterns. Not random firing, but clusters of signals that appear to come at somewhat regular intervals. We do not know what causes fast radio bursts. There are natural hypotheses, magnetars, colliding neutron stars, cosmic string interactions. But none of them completely, cleanly, satisfyingly explains every observation. And the patterns some repeating FRBs seem to show, well, we don't know what that means. We are listening to a universe that is broadcasting signals we cannot fully decode. And then, beneath all of this, woven into the very fabric of the cosmos, there is the deepest mystery of all: dark matter and dark energy. Here is the truth that took decades for cosmologists to fully accept. Everything we can see, every star, every galaxy, every nebula, every planet, every atom in your body, accounts for only about 5% of the total energy and mass in the universe. 5%. The remaining 95% is something else entirely. About 27% is dark matter, a substance that has gravity, that shapes the large-scale structure of the universe, that holds galaxies together, but that emits no light, reflects no light, interacts with ordinary matter only through gravity. We have never directly detected a single particle of it. We know it is there only by what it does, by its shadow. And the remaining 68%? Dark energy, an unknown force that is causing the expansion of the universe to accelerate. Not just expand, accelerate. The galaxies are not just moving apart. They are moving apart faster every moment. And we do not know why. We do not know what dark energy is. We call it dark energy because we needed a name, and because it fills the darkness, and because we are honest enough to admit we are in the dark about it. So when we look at the universe, when we stare out at all those hundreds of billions of galaxies, we are only seeing 5% of what is actually there. The universe is wearing a mask, and we cannot take it off. We don't even know what kind of face is underneath. Now we have to go somewhere uncomfortable. We have to ask the question that the size of the universe makes unavoidable. If the universe is this vast, if there are 200 billion trillion stars, if there are likely hundreds of billions of planets in our galaxy alone, if the universe is 13.8 billion years old, with billions more to go, then where is everyone? This question was first articulated, or at least famously posed, by the physicist Enrico Fermi, sometime around 1950. He was sitting at lunch with colleagues, discussing the possibility of extraterrestrial life, when he simply looked up and said, "Where is everybody?" It became known as the Fermi paradox, and in the decades since, it has never been resolved. The math is overwhelming. If even a tiny fraction of the stars in our galaxy have planets, we know they do. If even a small fraction of those planets are in the habitable zone, we know some are. If even a small fraction of those develop life, we don't know, but the numbers are huge. If even a tiny fraction of that life becomes intelligent, the universe has had billions of years to run this experiment. The result should be a galaxy teeming with civilizations, ancient ones, young ones, everything in between. A civilization that began just 1 million years before us. 1 million years, a heartbeat in cosmic time, would have had time to colonize the entire Milky Way, even traveling at a fraction of the speed of light, even stopping to rest, to grow, to build, and yet we listen, and the sky is silent. There are many proposed solutions to the Fermi paradox. Some are comforting, some are not. Let's talk about the ones that aren't. The first is called the Great Filter. It is perhaps the most chilling idea in all of science. The Great Filter is the idea that somewhere in the long chain of steps required to go from a planet to a galaxy-spanning civilization, there is a step so difficult, so improbable, so lethal, that virtually no species makes it past. A filter, a barrier, a wall that almost everyone hits and does not cross. Now, here's the terrifying part. We don't know where the filter is. It could be behind us, or it could be ahead. If the filter is behind us, if the hardest step was, say, the emergence of the first self-replicating molecule from raw chemistry, or the evolution of the eukaryotic cell, or the development of sexual reproduction, then we got lucky. Impossibly lucky. But we are through the filter, and the future might be open. But if the filter is ahead of us, if the hardest step is something that advanced civilizations always face and almost never survive, then the silence of the cosmos is not peaceful. It is a warning. What could the great filter ahead look like? Nuclear war. A self-inflicted extinction before a civilization can escape its homeworld. Artificial intelligence that gets out of control, replacing or destroying its creators. A pandemic engineered or evolved past any defense. Climate collapse. Resource exhaustion. A technological catastrophe we haven't yet imagined. Or maybe, and this one is particularly unsettling, maybe the filter is something external. A gamma ray burst from a nearby star, sterilizing a planet in seconds. Gamma ray bursts are the most energetic explosions in the known universe. A long-duration gamma ray burst pointed at Earth from within a few thousand light-years could strip away our ozone layer, would bathe the surface in lethal radiation, would collapse the food chain. We live in a galaxy that occasionally fires these things. We have no warning system. We have no shield. Or consider the asteroid. The same kind of impact that wiped out the dinosaurs 66 million years ago could happen again. Earth has been struck many times in its history. The rock that killed the dinosaurs was about 10 kilometers across. There are larger ones out there. We track many of them, but not all of them. Not nearly all of them. Then there is the dark forest hypothesis. This idea comes partly from science fiction, specifically from the Chinese writer Liu Cixin, whose novel, The Dark Forest, gave it its most vivid expression. But the underlying logic is cold and real. Imagine the universe as a dark forest at night. Every civilization is a hunter, moving through the trees. The forest is silent, but it is not empty. Every hunter knows others are out there, and every hunter knows this. Resources are finite. Life competes, and any civilization advanced enough to pose a threat, no matter how distant, no matter how peaceful seeming, is an existential risk. So what does every hunter do in a dark forest when they don't know if the other hunter is friendly? They don't call out. They don't show themselves. They stay quiet. And if they detect another hunter, they strike first, before they can be struck. The dark forest hypothesis proposes that the reason the universe is silent is not because we are alone. It is because every civilization that has ever reached a certain level of technological sophistication has realized the same terrifying truth. Silence is survival. Revealing yourself is death. Under this framework, what are we doing right now? With our radar, with our television and radio signals, bleeding out into space for the past century, with our active SETI transmissions, with Voyager 1 and Voyager 2 carrying golden records and precise maps to our location. With the message we beamed toward the globular cluster, M13 in 1974, the Arecibo message, telling anyone who might be listening exactly where we are. Under the dark forest hypothesis, we have been screaming our location into the dark. We want to be very clear. This is a hypothesis, not a consensus, not even a widely favored one among scientists. Most researchers who work on SETI and astrobiology do not believe the dark forest is the explanation for the cosmic silence. But the question it asks is real, and the silence it describes is real. And on a cold, clear night, when you look up at the stars, it is a thought that is very, very hard to shake. Let's talk about the last of the dark solutions, the one that doesn't involve anyone hunting us, the one that is, in some ways, the loneliest answer of all. We are alone, not alone on Earth, not alone in our galaxy, alone in the universe, or close enough to alone that it makes no practical difference. The rare Earth hypothesis proposes that the conditions required for complex, intelligent life are so extraordinarily specific, so demanding, so statistically unlikely, that we, here, on this pale blue dot, might be the only example, or one of a vanishingly tiny number. Think about what Earth has that other planets don't. A large moon, which stabilizes our axial tilt and creates the tides that may have been critical for early life. A Jupiter-sized planet in the outer solar system, which acts as a gravitational shield, deflecting asteroids and comets that would otherwise bombard us far more frequently. A liquid iron core, generating a magnetic field that protects us from solar radiation. Plate tectonics, which recycles carbon and nutrients, keeping the climate stable over billions of years. The exact right distance from an unusually stable, long-lived star. And billions of years of time, stable time, for evolution to slowly, painfully, miraculously build from single cells to philosophers. Any one of these factors is fortunate. All of them together, in the right combination, at the right time, in the right galactic neighborhood. Maybe we are the miracle. Maybe the silence isn't a mystery to be solved. Maybe the silence is the answer. And then there is the final implication of cosmic scale. The one that comes not from the silence, but from the distance. Even if there are other civilizations out there, even if the galaxy is full of them, each one waving at the others, each one transmitting signals, each one hoping to be heard, the distance between us may be insurmountable. The nearest star system to Earth is Alpha Centauri, about 4.37 light-years away, at the speed of the fastest spacecraft humans have ever launched. NASA's Parker Solar Probe, which briefly hit about 430,000 miles per hour. It would take roughly 6,300 years to reach Alpha Centauri. The Milky Way is about 100,000 light-years across. The nearest large galaxy, Andromeda, is 2.5 million light-years away. Even at the speed of light, the universal speed limit, a speed no ship carrying matter can ever actually reach, crossing our galaxy would take 100,000 years. The universe is not just vast in size, it is vast in separation. Every civilization that might exist is marooned on its own island, separated from every other island by an ocean so wide, so deep, so dark, that crossing it seems impossible. And yet, we sent Voyager 1 into space in 1977. In February 1990, at Carl Sagan's request, it turned its camera backward, from a distance of about 6 billion kilometers, and it took a photograph. In that photograph, Earth is a pale blue dot, not even a full pixel, a mote of dust suspended in a sunbeam. Sagan wrote about that photograph, and what he wrote is worth sitting with. He said something like this: "Look again at that dot. That's here. That's home. That's us. Every king and peasant. Every young couple in love. Every mother and father. Every inventor and explorer. Every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. On a mote of dust, in an ocean of 200 billion trillion stars." That image breaks you open, but we think it also, somehow, puts you back together. Differently. Better, maybe. We've gone far out tonight. We've gone to the edge of the observable universe. We've stood in the great void. We've heard the silence that follows the wow signal. We've felt the weight of the Fermi paradox and the great filter. Now we come back. We come back to this planet, to this moment, to right now. Because here is the thing about all of that cosmic vastness, all of those dark implications, all of that silence and scale and existential weight. None of it changes what happens here. And everything that happens here, everything we do on this small, fragile, shockingly beautiful world, matters. Not in spite of the scale of the universe, because of it. We are, as far as we know, the only creatures in the observable universe who look up at the night sky and ask why. Who build telescopes and aim them at the dark. Who write down what they see and share it with each other. Who feel, truly, deeply feel, the weight of 13.8 billion years of cosmic time bearing down on them, and respond not with despair, but with curiosity. That is extraordinary. That is, by any measure we have, a miracle. Let's talk about where we are, right now, as a civilization. Because the context matters. We are a Type 0 civilization. Just barely past Type 0, really. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by energy use. A Type 1 civilization uses all the energy available on its home planet. A Type 2 civilization harnesses all the energy output of its star. A Type 3 civilization uses the energy of its entire galaxy. We are at roughly 0.73 on this scale. We don't even fully harness Earth's available energy yet. We are nowhere near Type 1. And yet, what we have built in the last 300 years is astonishing. 300 years ago, we didn't know the universe had other galaxies. We thought the Milky Way was everything. We thought the stars were lights fixed to a crystal sphere. We thought the sun might orbit the Earth. 300 years ago, we had no electricity, no vaccines, no antibiotics, no engines, no computers, no planes, no understanding of DNA, no knowledge of atoms, no theory of gravity beyond the intuitive. 300 years is nothing, a breath, a heartbeat in cosmic time. And look where we are. We have placed robots on Mars. We have photographed a black hole 55 million light-years away. We have detected gravitational waves, ripples in space-time itself, caused by two black holes merging over 1 billion years ago. We have mapped the cosmic microwave background radiation, the literal echo of the Big Bang, the afterglow of creation, still faintly warming the universe 13.8 billion years after it was released. We have sent spacecraft beyond the heliopause into interstellar space. We have discovered thousands of exoplanets, some of them possibly capable of hosting life. We did all of this with bodies designed for running across the African savanna 300,000 years ago, with brains that evolved to track predators and find water and remember the faces of our tribe. With these brains, we reached out and touched the edge of forever. Now, here is where the cosmic scale comes back to Earth with full force. Here is why tonight matters. The Great Filter. We talked about it. We talked about how it might lie behind us, in the impossibly rare emergence of complex life, or ahead of us, in some catastrophe that terminates advanced civilizations. If the filter is ahead of us, what form does it take? What are the real risks? Climate change, not as a political talking point, as a physical reality. The Earth's atmosphere is a thin, fragile layer, barely 100 kilometers deep. If you could drive straight up at highway speed, you'd reach the edge of the atmosphere in about an hour. And we have changed its composition measurably in a geological blink by burning carbon that took millions of years to bury. The consequences are playing out in real time. Nuclear weapons. We have built enough of them to end complex life on Earth several times over. Not once, several times. They sit in silos and submarines right now, tonight, as you listen to this. Maintained by bureaucracies, guided by politics, held back by agreements and treaties that could, in principle, fracture. Pandemics. We saw what a novel pathogen could do to global civilization in 2020. Imagine something more lethal, more transmissible. Imagine one engineered rather than natural. Biotechnology is advancing fast, faster than our governance frameworks. The tools to design dangerous pathogens are becoming more accessible every year. Artificial intelligence, not the AI of science fiction, not a malevolent robot uprising, but something more subtle and more real. AI systems powerful enough to transform economies, militaries, information ecosystems, and power structures faster than societies can adapt to them. The question of how we align powerful AI systems with human values is one of the most important open questions in the history of technology. And we are, right now, in the middle of trying to answer it. Asteroid impact, space weather, supervolcanoes. These are lower probability risks, but real ones. And we have the technology, in principle, to do something about the first one, if we choose to prioritize it. Here is what the size of the universe tells us about all of this. In a universe this vast, this old, this full of possibility, the emergence of a civilization that can ask questions about the universe is precious beyond ordinary words. Not precious in the human-centric sense of, we're special because we're us. Precious in the scientific sense. Precious in the sense that complexity is rare. That consciousness, whatever it is rare. That the ability to build a telescope and point it at the sky and understand what you're seeing is, as far as we can tell, extraordinarily, perhaps uniquely, unlikely. If we destroy ourselves before we learn to be a Type 2 civilization, before we spread beyond this single fragile planet, before we answer the questions the cosmos has been quietly posing to us for 13.8 billion years, then the universe loses something it may never regain: a pair of eyes, a consciousness turned outward, trying to understand. We are the universe becoming aware of itself. That is not a poetic abstraction. That is physics. The atoms in your body were forged in the hearts of dying stars. You're made of star stuff, as Carl Sagan said. The universe created stars, and stars created atoms. And atoms came together on this planet in exactly the right way to create something that can look back up at the stars and wonder. The universe is looking at itself through your eyes. Right now, tonight. That comes with a responsibility. We don't say that to be dramatic. We say it because it is, quite literally, the situation. The choices we make, collectively, as a civilization, in the next 100 years, will likely determine whether we survive the next 10,000. Whether we become a spacefaring species or a cautionary tale written in geology. Whether we answer the question of whether we are alone or whether we become another silence in the dark. And those choices are made of smaller choices. What we build, what we fund, what we teach, what we value, how we treat each other, how we treat this planet, whether we look up or look down. The size of the universe is not an argument for nihilism. It is not evidence that nothing matters because everything is so small. It is the opposite. Because of how vast the universe is, the fact that anything like us exists at all is so improbable that it deserves, perhaps demands, to be protected, nurtured, extended, carried forward. We have seen, in our own lifetimes, what happens when humanity turns its full attention to a challenge. In the 1960s, fueled by a dream and a declaration, we went to the moon. From the first controlled aircraft flight to setting foot on the moon, 66 years. 66 years. In 2021, the James Webb Space Telescope was launched. It sees light from galaxies that formed just 300 million years after the Big Bang. It is peering back to within a heartbeat of the beginning of everything. In 2017, we detected gravitational waves from two neutron stars merging. We simultaneously saw the light from that merger with optical telescopes. It was the first time we had ever heard and seen the same cosmic event at the same moment. Astronomers wept, literally wept, because they were listening to the universe with a new sense for the first time. We are capable of incredible things. We are capable of standing at the edge of the unknown and building bridges into it, plank by plank, telescope by telescope, equation by equation. The universe is 93 billion light-years across as far as we can see. It may be infinite beyond that. It is 13.8 billion years old. It contains 200 billion trillion stars. It is 95% mystery, made of dark matter and dark energy we don't understand. It is silent, and we don't know why. And we are here, small and short-lived and made of atoms that were once inside of stars, with our questions, with our telescopes, with our voices, talking to each other in the dark. That is not nothing. That is everything. We don't have an answer for you tonight. We want to be honest about that. We don't know if we are alone. We don't know what dark matter is. We don't know what dark energy is. We don't know what lies beyond the observable universe. We don't know if the universe is finite or infinite. We don't know what came before the Big Bang, or if that question even has meaning We don't know if there are other universes. We don't know what consciousness really is, or whether it is rare or common in the cosmos. We don't know if the great filter is behind us or ahead. We don't know who or what sent the wow signal. We don't know why Tabby's star dims the way it does. We don't know what makes the fast radio bursts. We don't know. And isn't that remarkable? In the history of our species, that feeling, the feeling of not knowing, was terrifying. The darkness before the fire, the silence before the language. But somewhere, maybe around the first campfire, maybe looking up at the first night sky, that feeling of not knowing became something else. It became curiosity, and curiosity became questions, and questions became science, and science became telescopes pointed at the dark. And tonight, at this moment, in the quiet of wherever you are, science has reached a point where the questions are bigger than they have ever been. We have answered so much. We know the age of the universe. We know the expansion rate of space. We know the composition of stars from the light they emit. We know the mass of black holes we have never seen. We know the temperature of the cosmic microwave background to 4 decimal places. We know so incredibly, astonishingly much. And the more we learn, the larger the mystery becomes. Every answer opens 10 more questions. Every telescope pointed further into the dark reveals that the dark is larger than we thought. That is not failure. That is what discovery looks like. Tonight, if the sky is clear where you are, if there are no clouds, and you are somewhere with just a little darkness, we want you to go outside. Just for a moment. Just to stand there and look up. You don't need a telescope. You don't need any equipment at all. You just need your eyes. The light hitting your eyes when you look at a star is ancient. The light from Alpha Centauri, the nearest star system, left its source 4.37 years ago. The light from the stars of the Big Dipper left its sources between 58 and 124 years ago. The faint smudge of the Andromeda galaxy, just barely visible to the naked eye on a clear night, shows you light that left its source 2.5 million years ago. When our ancestors, 2 million years ago, before language, before fire, before everything that makes us, looked up at that same smudge and felt something they couldn't name. That light was already 500,000 years old. When you look at the night sky, you're not looking at the universe as it is. You're looking at the universe as it was. A time machine built from photons. And somewhere out there, maybe around a star you can see with your naked eye, maybe around one so far away no human instrument has ever found it, maybe, just maybe, there is something looking back. Maybe they are asking the same questions. Maybe they have been asking for longer than our civilization has existed. Maybe they built their equivalent of radio telescopes 1 million years before we built ours, pointed them at the sky, listened, and heard silence too. Maybe they looked out at the vastness and felt the same thing you are feeling right now. That feeling has a name. It doesn't have one word in English, but it has a shape. It is the feeling of being small and vast at the same time, of being temporary and eternal at the same time, of being utterly alone and deeply, achingly connected to everything at the same time. It is the feeling the universe gives you when you finally really look at it. The universe is 93 billion light-years across, as far as we can see, maybe infinite beyond. It is made almost entirely of things we don't understand. It is older than our ability to truly feel. It is populated with more stars than grains of sand on every beach on Earth. And in the middle of all of that, for a brief, improbable, luminous moment, there is this, us, together, in the dark, asking why. We don't know if the silence means we are alone. We don't know if the wow signal was a greeting we missed or a coincidence we inflated with hope. We don't know what's on the other side of the observable universe. We don't know what came before the Big Bang. We don't know what the dark is made of. And we really, genuinely think, that this is okay. Not knowing is not a failure. It is an invitation. The universe is not a problem to be solved. It is a mystery to be lived. Every generation that comes after us will know more. We'll see further. We'll understand deeper. We'll carry the questions we could not answer into new light, new instruments, new mathematics, new dreams. And somewhere out in that darkness, 93 billion light years across, teeming with 200 billion trillion stars, silent and vast and impossibly ancient, the answers are waiting. They have been waiting for 13.8 billion years. They can wait a little longer. Tonight, go outside, look up, feel the size of it. Let it break you open, just a little. And then feel the warmth of the atoms inside you. Atoms forged in stellar furnaces billions of years ago, keeping you warm in the dark. You are made of the universe. You are the universe, looking at itself. And that is enough. For tonight, for right now, that is enough. Thank you for being here. Thank you for staying with us, in the dark, in the quiet. If tonight left you with something, a question, a feeling, a need to look up at the sky, subscribe, and come back. We'll be here, waiting in the dark, like the universe does, patiently, endlessly.